Welcome back to che205. In this video, I'll be talking about another example of solving second order or higher order differential equations without splitting into a system of equations of first order. This time we're going to use direct finite differencing to discretize the differential equation. So in the last video, we talked about second order differential equations, or the heat conduction problem with two boundary conditions on the two ends, right? In this example, we're going to look at the same problem, but instead of splitting the second order differential equations into two first order differential equations, we just discretize directly the differential term. So let's get to the details. That is section 6.3 on page 125 of the textbook. So to directly discretize the differential equation, we replace the left-hand side. Remember, the left-hand side was the second derivative of t with respect to x, right here, right? So we're going to replace the second derivative on the left side using central differencing. And to get this equation, refer to page 83 of the textbook. So if I go up to page 83, let's see, page 83, it's further down, this is it. So we are using central difference, and that is a second derivative approximation, right? For second derivative, we have to use the point ahead of us, minus 2 times the current point, plus the point before us, divided by del x squared, okay? By the way, the first order approximation doesn't have central difference version. So I'm going to go ahead and do that on page 125, which should be right here. Yep, okay. So let's see, so this, yeah, so further up, yes, this is it. So this is the central difference version of second derivative of t with respect to position, right? A point ahead of us, minus 2 times the current point, plus the point before us, divided by del x squared, and that's the right-hand side. Everything on the right-hand side is at point I. Okay? So then we have two boundary conditions. At T0 is 100, the other temperature at the other end is 0. Okay, so that is, if I discretize my domain to n points, n plus 1 points, or n intervals, then t at n plus 1 is 0. Okay, so we're going to plug in I here from 1, 2, 3, all the way to n. And we're going to write these equations one by one. Okay, so let's assume delta x is 1 over n plus 1, and for simplicity, and then we're going to lump these coefficients for h over dk as another coefficient called a, right? And so now we're going to plug in I equal 1, right? So for I equal 1, we're going to have t0 minus 2t1 plus t2, where del x squared is a times t1 minus ta, where I is 1 here. Okay? We reorder this. We know t0 is 100, so I'm going to plug in 100 here. We multiply through by del x, keep t1, t2 on the left side, group this t1 with that one, and then at the end of the day we get this equation. Alright, fine. Now let's make this a bit shorter. I'm going to call 2 plus a del x squared is t1. Sorry, that means I'm going to call this b, and then call a del x squared ta as c. Okay, these are all known, right? A is known, del x is known, ambient temperature is known, and same thing here. So that's why b and c are two known constants. So with that, this equation can be written as b times t1 minus t2 is equal to c plus 100. Okay? We redo the same thing when I is equal to 2 now. So this was I1. We're going to replace I by 2 and redo this simplification. This time we get, well, we're going to crank up all the indices right here by 1, so it's going to be t1 minus 2t2 plus t3 divided by del x squared is equal to a times t2 minus t8. Then multiply by del x squared, use these constants, and at the end of the day we get this equation, another equation, right? So t1, t2, t3 involved. So we keep doing this. I'm going to plug in I equal 3, 4, 5 all the way to the n, and when we put in, we get this equation, right? And we do the same thing, multiply by del x squared, move unknown to left side. Now this time tn plus 1 is known because that is 0. Right? That is the boundary condition right here. Because that is known, we keep it on the right side. Alright, so this is going to be on the right side at the end. And anyways, that's 0, so you can put just 0 here. And tn and tn minus 1 survive, so that's the last equation I have. So the last equation is a bit different. Right, look at that. So from equation 2 to n, or from 2 to n minus 1, the equation looks like this with 3 variables, t1, t2, t3, or ti minus 1, ti, and ti plus 1. For the last one I have 2 unknowns, and for the first one I also have 2 unknowns. Alright, so we're going to put all these into the spreadsheet and use matrix package or syslin to solve for the system. So here is the solution. I have hdk, a simplified version of 4hdk as a lump constant. Ambient temperature n is 9 because I have 9 intermediate points. With the interval of 0.1, I have 11 points, or 9, well, 11 points including the 2 endpoints, which means I have 10 points, but 9 of them are unknown in between, right? The first and the last are known, so the 9 points in between are unknown. That's why n is 9. A, B, C are these constants that we derived in the textbook, right? So this is C, let's see. This is C, this is B, and this is A, which is 4h divided by dk, right here, okay? So with that, we put all the equations in here. The first one is, let's go over a couple of them. So the first equation is b times t1 minus t2. So here is b, right, times t1. So that's the first equation. First column is the coefficient for t1. Second equation is the column, or second column is the coefficient for t2. Third column is the coefficient for t3, all the way to the end, where I have here t. This is the coefficient for t10, right? And then the last one actually supposed to be the coefficient for t11, which is the last point, but I know that the temperature, so I don't put that into this matrix. So this matrix has the coefficient from let's say t1 here all the way to t9. Okay, t1 or t0, which is the 0 temperature, and t10, which is T0 is 100, sorry, T10 is 0, I know the temperature, I put everything else in between. And these are the coefficient corresponding to the unknowns, which is T1 through T9. Okay, in the first equation, the coefficient for T2 is minus 1, right? So here's minus 1, move it to the side. So that is minus 1. And then the right-hand side is 100 plus C, and C is 3.25, so 100 plus C is 103.205. Okay, we go to the next equation. We have minus 1, B minus 1, so here's minus 1, B, which is 2.128, and then minus 1. The right-hand side is going to be C, which is 3.205, so here's 3.205. This is the right-hand side, C, right? So it's A times some unknown vector, which is T1 to T9, right? So A times T1 to T9 is equal to vector C here. Okay, Then other equations, as we discussed, would be similar to this, so that's why these coefficients repeat with a shift to the right side, you see that. Except the last equation. The last equation is minus t n minus 1, and if I have, let's say n, maximum n is 10, so this is going to be t9 minus t9, and then plus b times t10. So here's minus t9 plus b times t10. b is 2.128. Right hand side is still as c, which is 3.2. Okay, so I have a matrix. This is my matrix of coefficients. These are the right hand side. I have to go ahead with the matrix package and solve for temperature. So what I do is, so I'm going to click on matrix package, if you remember that, and then go to macros, matrix operations. I want to solve the system. So here's ax equal b. My matrix coefficient would be from here to here. My b coefficient would be from here to here. And the result, let's say I want to have a result right here. Right, so here it is. The solution is exactly as I had before. The first and last, I put manually the temperatures here. 100 here and 0 there. Is a known, right? Okay, so this is the temperature I get, which I have here. Okay, then we're going to go ahead and plot the temperature. So here's temperature against the, well, temperatures against position. So you get this curve. It's 100 on the left end and 0 on the right end. So we solved it without even splitting the differential equations. Now, we can change the boundary condition to something slightly more difficult. Like in the next case, and the textbook actually discusses that. If, let's say, I have same differential equations, but this time I'm going to give the temperature at x0 100, and then the other end is insulated. So if insulated, that means there is no flux, means the derivative of temperature with respect to x is 0. So down the type of the boundary conditions are different. This one is given for temperature, this one is given for the flux or the derivative. So what should we do? Well, almost all of the equations are the same as what we did before. The only thing is how we implement the last equation, which is for this differential equation, right? And to do that, we have to use finite difference version of this. So we look at page 83. So go back up to page 83 again. And so here it is, page 83. And so I want to do second order approximation. For the right end, I have to use backward difference because every point before me is known. So I'm going to use this equation. We cannot use forward difference because if you put this guy at the boundary point, you need to know 2 points ahead of the boundary point, which is not available. So then we're going to use backward difference, and that would be 3 minus 4 plus 1 divided by 2 del x. Okay, so 3 minus 4 plus 1 divided by 2 del x. So we're going to go back to page 126 or so, okay, on chapter 6. So here it is, and this time we're going to have a different boundary conditions. Okay, so let's see. Okay, so for this one I have, let me write it here. So it's going to be it's going to be 3 times, okay, so 3 times, let's say I have n plus 1 points, right? So it's going to be t n plus 1 minus 4 times tn plus tn. I'm sorry, this should be minus. That's right, that's right. So n plus 1 and n minus 1. And all of them divide by dx, that's equal to 0. So that means the numerator has to be 0, and then you can put the equation for the last relation right here into the spreadsheet. So it's going to be 3 minus 4 and 1. And that's what I have, 3 minus 4 and 1 here. Okay, so stay tuned. In the next section, I'm going to explain in details how we got the last equation. Thanks for watching.